Hi everybody, and welcome to the next video on SIR models. Let me start by saying that these slides are available on Moodle, so you can grab them yourself if you want to, take notes if you want to as we move along. Also, I'm going to try to keep this video as brief as possible, so I apologize if I move too quickly. So make sure you ask me questions, or you can pause the video, of course, things like that. But in particular, let me know if you have questions on anything in class or via email. So in the previous video, we set up the general SIR model with B and K and so on, but we didn't actually solve anything. We didn't actually look at an example of any particular disease, any particular outbreak. So in this video, I want to show you an example of a disease. So we'll build a specific model, we'll solve it, interpret the results, and then check the model against the actual data. So we'll actually do the full 4 steps of a math modeling problem. Whereas last time, we actually didn't even do this. We built the general model. We didn't plug in values for B or K or anything. This time we're doing the whole shebang, everything. So build a model and solve it. The example we're going to do is from the late 1960s when the US was swept by a pretty deadly strain of flu called the Hong Kong flu. This strain of flu was the most deadly the United States had seen since the 1918 pandemic. And we actually haven't seen anything like this since until the coronavirus pandemic that we're in now. This strain of flu killed 100,000 people or so in the U.S., which when you adjust for population growth is like 150,000 or 170,000, something like that today. So it was a pretty serious strain of flu. So we're going to look at an example of an outbreak of this in New York City in the late 1960s. Also worth noting, no flu shot back in the day. So this maybe wouldn't have been so serious if it happened today, but very serious at the time. I should say we're going to start with this example because the data is clean and known. So this example here is not particularly timely or topical. An example from the 1960s. We're starting with this one just to get our feet wet because it's such a known entity. This flu has been very well studied. So we'll talk about COVID-19 later. You know, we're a year and a half into it or whatever now, but it's still not super well understood, especially relative to these older outbreaks. Okay, so here's what that flu outbreak looked like in New York City. So here's a frequency table of deaths by week. So what we're going to assume is that deaths are a lagging indicator for actual cases. So in the SIR model, there was no variable for number of deaths. There was a variable for number of infected people. So we're going to assume that the number of deaths track with the number of infected people but lags a week. So notice the deaths peak in week 6. We're going to assume that means the infections peak in week 5. So that means we'll assume that week 5 actually had the most sick people. So the epidemic itself, the outbreak actually, why is it doing that? The epidemic peaked in week 5. We're just seeing that peak a week later manifest in deaths. So that's what we're going to assume. So when we check our model later, we're going to check against this, but we're going to check if our infected curve, if the number of infected people peaks around week 5 or not. So here's the complete SIR model from last time. This is the proportional version. So notice there are no capital letters here. So B was the effective contact rate, K was the number of days that an infected person has the disease and can spread it, and so on. So what we need to do now for this particular outbreak is plug in B, K, S naught, I naught, and we're assuming that nobody's had the disease yet, so we know that R of 0 is 0. So there are 4 things we have to plug in here that we don't know. So in the case of the flu, and in particular the Hong Kong flu, usually you're sick with that for like 3 days on average. So the typical person can spread the disease for about 3 days. The flu is not particularly contagious, so we'll start with a B value that maybe is on the lower end, although you don't really get a sense of what's low or high until you play around with these things for a while. But we'll just start with a B value of 0.5. So for this particular virus, like nobody was immune at the beginning in New York City, we'll assume some small amount of people were initially infected. This number doesn't really matter. 10 versus 5 won't make a difference in the model we build, really. So now for our initial values, the population of New York City at the time was 7.9 million people. So if 10 people are initially infected, everybody else is susceptible, nobody has recovered at time 0, And then if you want the proportional model, you would translate those raw numbers like this. So the initial amount of the initial proportion of people susceptible is like everybody. The initial amount of infecteds, the initial proportion of people infected is very close to 0, but not 0, and the initial proportion of recovereds is 0. So here's the complete proportional model for the Hong Kong flu. I just plugged in my B value, K value, S naught value, and I naught value. So again, if you want to be persnickety here, you could put a 0.999999 there if you wanted to. It doesn't make a difference in what the computer does. Now, if you round this down to 0, that will make a difference, of course, because if nobody's infected initially, the infection curve can't take off. But anyway, this is now an SIR model that we could solve. And when I say we can solve it, I actually do kind of mean we. We could solve this if we felt like it. We can't solve it theoretically because this is not a linear model. So because you have S times I here, not like S plus I, if this were S plus I and then S plus I, this would be a linear model. But because we have S times I, it's a nonlinear model, so we can't use chapter 7 here, unfortunately. So since this is a nonlinear model and we can't solve it using any tools we have, we'll have to approximate solutions. And the way you approximate solutions to systems of differential equations like this is Euler's method. If we were in class, I would make you guess that. And then when we all said Euler's method, you would all gasp in surprise and pleasure, I suppose, right? Just seeing that come back from before the last exam. So when I say we'll use Euler's method, I of course mean a computer will do it for us. So as you have seen, Euler's method is not interesting to use. It's tedious and repetitive. So we're not going to use it ourselves. We'll outsource it to a computer. So let me show you how we're going to outsource it to a computer. So if you go to Moodle, you'll see there's a link here called Online Python Compiler. So open that. When you open it, I should say it probably won't look like this to you. See how there's a bunch here already? For me, it remembers that I've been messing with it earlier, so it autofills a bunch of this stuff. But for you, it's probably going to look like this maybe. I don't know. It's going to have just a little bit of code here. So the first thing you should do is select everything and delete it. So just clear it out. There should be nothing here. And then you should go back to Moodle and see how there's an SIR Python code file that says 4 proportion plots. You should download that. So for me, it opens like this. And what's in this file is a bunch of Python code. So those of you who've had Python before, like Grant or Ben or Jacob Clark, people like that, you'll recognize some of this, not all of it, because we didn't solve ODEs in DTS 190. But anyway, so here's just a Python script. Now I should say, by the way, you don't have to know any Python to use this. So don't worry if you don't have any programming skills. I don't assume you can program. You're just going to make tweaks in the code like where I'll show you. So you should copy and paste this. Select it, copy it. So I just Control-C, so I copied it. And now you should paste it into this window over here. See, all that code is there now. This is the code we're going to use to run Euler's method to get us proportion plots for SIR models. This code here, right here, is actually where it solves it using Euler's method. So you don't see the word Euler in here anywhere, but it's embedded in this command, this solver down here. Okay, but you're not going to worry about that. So for most of this material, you're not going to mess with this at all. So you don't even look at that. The stuff you're going to mess with is up here, and this you're barely going to mess with. We'll mess with this later next week sometime. So let me just show you what all is here. This capital N is the total population that you're interested in right now. So I already have the 7.9 million there. Here's I naught and R naught. Notice these are actually capital letters here. Okay, so capital I naught, capital R naught. So even though these are proportional plots, you're still going to hand it the raw numbers for the initial values. That's kind of confusing, but it saves you from having to type 1.27 times 10 to the negative 6. You know, that's kind of obnoxious to type. So this code later, it takes these and divides them by 7.9 million to get those initial proportions. Okay, so I naught and R naught are 10 and 0. So if the problem were something else, you know, if you had like 500 initial infecteds, and for whatever reason, maybe you have, you know, 5,000 initial recovereds, you would change them like that. Okay, so 10. I wonder if I can make this bigger. Oh, I can. Okay. Then you don't have to fill in S naught because S naught is just N minus I naught minus R naught. Right here is where you tell it what B and K are. So B in our problem was 1/2. So I'm going to type 0.5 there. You could, of course, type 1/2 if you wanted to. K was 3. And the last thing you'll mess with for now is, notice this variable here says number of days. So you can tell it how far into the future you want it to look. So I've asked it to look 150 days into the future. You could ask it to look, 15,000 days into the future. But as you might imagine, the farther into the future you go, the less reliable the model is going to be. So you got to be a little careful about that. And then what this does, actually, you're not going to mess with this, but this sets up the time step for Euler's method. So anyway, Euler's method is here. All of that to say, once you do this, the total population, the two initial values for I and R, capital, B and K, the number of days you want, then you click Run, and notice what it does. It creates a plot for you. Creates 3 plots for you, 3 curves, and these curves, again, were made by Euler's method. Very nice. So Euler, of course, came up with his method like 200 years ago or something. He didn't have computers then, but now that we have computers, just boom, right? I clicked Run, and it made this in like half a second. That's super nice. Anyway, so now you can see how the epidemic goes. So this red curve here is the infected curve, as it says. Blue is susceptible curve. R is recovered curve. And these, of course, are proportions or percentages, it says. So initially, 100% of the population is susceptible. Initially, nobody is recovered. And initially, basically, nobody is sick. Right? That's why we're down here at 0. Then around day 50 or so, notice the red curve starts to really tick up to a point where it's noticeable to our naked eye here. The epidemic peaks around day 78, and it's hard to tell from the scale, but it looks like somewhere between 5 and 10% of the population is sick right here. So that's a lot of people sick at once. If it's 10%, that's 790,000 people. And then by the time you get to day 100 or so, the epidemic peters out. The outbreak is basically over on day 100. So you can, among other things, notice how many people get sick. Like if I asked you, hey, over the course of this epidemic, how many people got sick in total? Well, you can, for example, watch this blue curve fall. So the susceptible curve only can fall because we don't add susceptibles to the population, as we discussed in the previous video. So initially, everybody is susceptible, everybody but those 10. And then the curve over time falls. And of course, as the red curve picks up steam, that's causing this blue curve to fall. And then, see, when the epidemic sort of peaks, that's when we reach an inflection point. A nice Calc 1 word here. An inflection point in the S-curve, and things start to turn around. So it's still falling, but not falling quite as quickly. It's decelerating here. And then the deceleration is complete somewhere around here. It flattens out. So anyway, you start at 100% and fall to something like 45% or so. So at the end of the outbreak, 45% of the population is still susceptible. That means 45% did not get sick. Therefore, 55% did get sick. So you can just look at these graphs and say, oh, because the blue curve fell by that much, I know 55% of the population got sick according to this model. Now, one last thing to point out about these pictures is that they look smooth, don't they? But again, they're not smooth. These were stitched together by tangent lines, as we discussed with Euler's method. So they look smooth to us because the time step is small enough that our eye can't see it. But again, these were stitched together tangent lines by Euler's method. Okay, now I want to show you one more thing with the code. So notice there's another one here. There's actually 2 more. This one we don't care about for now. This one here, SIR Python code for raw numbers. So if you don't like dealing with the percentages, you can deal with the raw numbers. Let me grab this. So I'm going to copy this. I'm going to get rid of all this. That's gone. Paste in the other one. There's not much different here in terms of what you guys will type. So see total population, I naught, R naught, where again these are capital letters. More natural to use those now because these are for raw numbers. B and K, number of days. Nothing changes in terms of what you hand the code. What will change when you hit run is what the code shows you. So I'm going to hit run. notice the curves are basically the same. It's just the scale is different, right? So you go from not 0 to 1, but from 0 to like 7.9 million because it's raw numbers. And now we can actually watch. Oh, oops, sorry. I forgot to change my B value. It wasn't 0.65, it was 0.5, sorry. So this actually does look a little different than before. Yeah, okay. Now these look much closer to what was before. Anyway, so now you can watch the blue curve fall from like 8 million or so to 45% of the population is like 3.5 million. You can see that. So again, it just depends on what you want. Do you want raw numbers or not? But the curves will be the same. Now, the one nice thing about this program that was not in the other code is that, see up here, it tells you approximate number of people who got sick. It'll just spit out the number for you. So this is approximately whatever I said, 45% of the population or something. From the curves, it's a little hard to eyeball these sorts of things, right? Because the scale isn't super great. So if you want to just know how many people got sick over the course of the entire outbreak, this script will tell you here if you run the raw numbers one. So this many people got sick. So sorry, this is 55% of the population is how many people got sick. So 45% of the population did not get sick. Anyway, so again, it's really nice what these programs these days can do. So when I was a student, we had none of this. Literally no access to this. The people who could do this back in my day were like, NSF funded researchers at Harvard had computers that could do this. But this was this was not accessible to somebody like me. Now you guys can go online and just like boom, hit this button and it just does it. It's amazing. Anyway, so here is a snapshot of that Hong Kong flu outbreak in New York City according to this model. Okay, with these particular parameters, B of 1/2 and K of 3 and so on. Okay, so let's hop back over into the slides now. So we solved the system. Oh yeah, I want to think about how many people died. So the death rate was, for every 100,000 people who got it, 17 died. So let's think about that. How many people got it? Well, the model told us this. That's how many people got sick. The death rate of the disease is 17 per 100,000. So you would do this little computation here, right? Number of people who got sick times this, like basically a proportion of people who die of people who get sick. And you would predict, based on the model we just built, 781 people would die. Now, if you go back to the original data that we started with, this number is not great because the actual number of deaths was this, if you go back to the original table. So, 781, 1,035, they're kind of close, but in terms of like an error percentage, they're way off. This is not good. It could be worse, but this is not a good model that we built. And furthermore, our model gets the timing all wrong. So our model shows the epidemic starting at like day 55 or day 60 or something. But in the actual data, like we said, the deaths peaked in week 6. So we're just off. Our timing is off. The picture we got here, the outbreak is taking off way too late relative to the data we had. So you got to do something about that if you're a modeler, So you got to say, well, the model I built didn't agree with the data, so what am I going to do? Well, you say, well, what could change in my model? Well, the number K, for example, we saw empirically. This is just known about the flu, so you can't change that. But the number B was just a guess that I made up. So, you could mess with that maybe. So let's increase it to try to get the timing better. So to increase something to 0.65, all you gotta do is come here, 0.65, boom. Run it again. And now see the model predicts the peak basically where the deaths, a week before the deaths peaked in our original data. And now the number of people who get sick is more, so we would predict more deaths. I don't know if we get exactly the number of deaths we actually got, but this now is much more in line with what we saw. And by the way, if you want to change the number of days, I already mentioned you can. But notice the epidemic is done by day 70 or something. So there's no reason to go 150 days out. If you want a better picture, you can just change that. And it zooms in for you. Okay. So now here, this is how many people got sick. the top of the program gave us that, and now you get 1,049 deaths, which overshoots the actual number, but just a little bit. This is pretty good. So no model is perfect, so if you get within 14 deaths out of thousands, that's pretty good. So we actually just ran through all 4 steps of math modeling. We built a model, we solved it. When I say we, I mean the computer, but that's fine. We interpreted the results. We thought about how many people got sick, how many people die, and then we compared what we got to actual data, and what we got was not great, so we updated the model. So that's sort of how things go. Now, if Hong Kong flu outbreaks in Chicago, you would try this, try this b-value, see how that goes. And if it works out pretty well, you'd say, okay, I think I have a pretty firm grasp on the effective contact rate for the Hong Kong flu. But then if it breaks in Chicago, you'd have to sort of monkey around with the numbers again, It's always sort of an ongoing process. Okay, so to conclude this video, I just want to ask this question here because the homework asked this. Does an epidemic occur? So in this situation here, I think we could all agree an epidemic occurred. Epidemic colloquially understood because like 6 million people got sick. If that's not an outbreak, or if that's not an epidemic, I don't know what is. But if you're going to be asked just in general, hey, did an outbreak occur here, or did an epidemic occur here, you need an actual working definition, or you can't answer the question. So in the literature, it's actually slightly vague what the technical definition of this word is, or the technical definition of an outbreak. But as best I can tell, in the literature I've looked at, basically, if there exists a local maximum in the I curve, that's what it means for an epidemic to happen. So what does that mean? That means that if your I curve ever ticks up ever, if you ever see an upward tick, well, then it has to be building to something, and then because people recover, it would eventually have to fall back down. So an epidemic occurs when you get this kind of picture to your I curve, even if it's super flat. An epidemic has still occurred, we say. So if I flatten this curve out, so it's really, really tiny, but there's still a little hump right there, that's still an epidemic. So by contrast, if there's no local maximum, that just means the curve only decreases down. That would be not an epidemic. So keep this in mind in your homework. To have an epidemic means initially the curve rises. So it's hard to see the rise right here, isn't it? It looks like it's flat, but it's ticking up ever so slightly, and then eventually it sort of takes off, gets to a peak, and then it'll taper back down. This is in contrast to, let me show you what not an epidemic looks like. Let's say that the disease is like super, super not contagious. So the lower you make B, the less contagious it is. Okay, so see what it's saying? 12 people got sick. So what does that mean? We started with 10. Those 10 people managed to get 2 people sick for a total of 12. And see how the red curve it looks flat to us, but it just goes down to 0 and dies out. This is what not an epidemic looks like. Now, again, you have to be a little careful because if you set your viewing window in a silly way, so here my viewing window was not silly. I saw up, down, but you can start to see how a viewing window might skew things for you, right? So what if I set my viewing window at 20 days? Why would you do that? I don't know, but suppose you did that. See, it looks flat, and it tells me only 500 people got sick, but this program just goes till the end of the time window. It's not looking into the future. So clearly, if you set your viewing window wrong, you can run into trouble. So you got to be a little careful about that. So you got to set your viewing window far enough so you can at least see an uptick. So if I set my viewing window at like 60, I shouldn't do that, but in my red curve, see how I see a little uptick there? That means, oh, it's going to peak somewhere later. So this is an outbreak. Okay, so at the end of this video, if I give you English that lets you plug in like a B and a K and these initial values, you should be able to use this code here to build these pictures. And that's what a lot of the homework is. You build the pictures, then you interpret them the same way we just did in these slides. How many people get sick? Was there an outbreak or not? If I give you a death rate, how many people die? Questions like that. Okay, so if you have any questions at all, make sure you email me or ask in class when we come back on Monday.